Part 3. The next topic is contact. Contact is one of the biggest differentiators of multi-body dynamics software, especially RecurDyn. I recommend you to compare the performance of contact when you benchmark FEM software or MFBD software. But contact is a little more difficult than other components, so you should understand contact parameters well to improve the accuracy and calculation speed of the contact model. Actually, many questions from users are usually about contact. RecurDyn contact is based on Hertzian contact theory. Even though Hertzian contact theory assumes the deformation of bodies, RecurDyn contact uses penetration instead of the deformation. In reality, there cannot be any penetration between bodies. Numerically, RecurDyn assumes that there can be penetration, and calculate the contact force by multiplying stiffness K to penetration. Simply speaking, if two bodies are overlapped, they push each other out. In addition, please note that RecurDyn uses tessellation to detect the penetration. The surface is divided into many patches to search algorithm to find out the penetration. And friction characteristics can be considered in RecurDyn contact. RecurDyn provides many types of contact. The most important and frequently used contact is this number 1, geosurface contact. Sometimes solid contact number 2 is useful too. Number 3, primitive contact is useful for the primitive geometries such as sphere, box, cylinder, and others. Number 4, the 2D contacts for 2D curves. These 4 contacts are legacy contacts which were developed a long time ago. They exist for the compatibility with the old version of RecurDyn or for student version of RecurDyn. Among the various contact types, let me give you a brief guide to choosing the contact type which suits your purpose. The most recommended contact type is geosurface contact. But when the contact surfaces are convex, then solid contact can be useful because it is usually faster than geocontact. If we define contact between spheres, then sphere-to-sphere or sphere-in-sphere contact can be used. This is the example of cylinder-in-cylinder and sphere-in-sphere contact. They use mathematical equation of the surface, so it is very accurate and fast. For 2D problems, 2D contact can give you better results very fast. For instance, if a cam follower is constrained by joints such as revolute joint, it doesn't have any 3D motion, so 2D contact is suitable for this kind of case. You can define 2D contact using edges of the geometry. This is the contact property page. Stiffness and damping coefficients are the important parameters of contact. Contact force parameter is very similar to spring force. Since stiffness is multiplied to penetration, the bigger stiffness is, the bigger contact force occurs for the same penetration. If large contact force suddenly occurs, it makes the solver unstable. So it is important to use the appropriate K. If big damping coefficient is used, the restitution usually decreases. So sometimes it looks sticky. It will be shown in the demo video later. And it is possible to use nonlinear stiffness and damping using spline. Please note that contact also uses base and action. Usually set the bigger and relatively stationary body to base. Like this image, set small body, sphere, to action body. Its patches are smaller than box. Contact friction is similar to joint friction, but the threshold velocity is a little different. Joint friction had one absolute threshold velocity, while contact friction has two threshold velocities, static threshold velocity and dynamic threshold velocity. This is a demo video about contact. There are two bodies. Without contact, the small box falls through the big box. Let's define a contact between them. Big box as a base and small box as an action. Contact occurs very well. RecurDyn contact uses tessellation data. Plane tolerance factor is the most frequently used parameter. But flat surface is not affected by plane tolerance factor. It is used for curved surface, like sphere. Bigger plane tolerance factor generates the coarser patches. Smaller plane tolerance factor generates the denser patches. For the flat surface, you can use max facet size factor. It affects the maximum size of the patch. This is the result with denser patches. This is the result with denser patches. You can find that the small box rotates. It's because the shape of the patches is not symmetric. If you use the quad type patch, the box doesn't rotate. Stiffness coefficient is similar to the spring coefficient, and damping coefficient works like stickiness. If the bigger damping coefficient is used, the bounce of the box is apparently decreased. So far, I briefly explained RecurDyn contact. There are more information you need to know to use the RecurDyn contact well. I recommend you to read these useful technical articles in function-based technical support site. One of the most frequently asked questions about contact is how to decide the initial value of stiffness coefficient. In fact, there is no absolute guide to the appropriate contact stiffness coefficient. Usually, it is decided by comparison with the experimental data. But there is one, not perfect, but a simple guide to decide the initial value. It is based on Hertzian contact formulation. FunctionBase provides a helper, so you just need to enter appropriate parameters to this Excel sheet, such as radius, Young's modulus, and Poisson's ratio of both geometries. Then the stiffness is calculated. This is workshop 9. You can use solid contact and geosurface contact to create a Geneva wheel model. The next topic is expression. It was already introduced briefly when I mentioned joint motion. Expression is used for force and torque, joint motion, user-defined result using request, parametric value or point, and it is also used for other functions such as on-off joint or stop condition. This is the expression dialog. You need to create expressions before you use them. You can input expressions in this way. At this time, you can use RecurDyn entities as arguments using their names, here, here. You can also use argument list. You can register the entities here first. Then, you just need to input argument numbers here. This argument list is very useful when the entities are used in one expression repeatably. Let me introduce a request. If we want to review the result of the expressions you made in plan mode, you need to create request. You just need to assign expressions in expression request dialog. Then, you can find the expression requests in plot database after simulation. Let me introduce the request. If we want to review the result of the expressions you made in plan mode, you need to create request. You just need to assign expressions in expression request dialog. There are expressions and you just need to assign expressions in expression request dialog here. Then you can find expression request in plot database after simulation. Since there are so many functions, help is an essential feature to use expression well. The format of the functions, their arguments are described in this help. You just need to select the function name and help menu to display help. Function Bay provides expression handbook. This handbook includes all helps about functions for expression. Similar to help, this handbook provides format, argument, formula, and examples for each expression function. You can download it from this link. Let me introduce what kind of functions are supported for expression. There are various functions, so let's just look over them here. Please read these pages carefully later. Since Expression Handbook includes more information than this, it would be better to read Expression Handbook instead of these pages. Okay, I believe you understand the arithmetic and relational operators easily. Plus, minus, multiplication, division, involution. Just note that how you can use involution in expression. These are frequently used constants: time, pi, dTOR, and RTOD. You are already familiar with time, and dTOR and RTOD are used to convert the unit of angle. Please note that there is a parameter called time offset for expression. You can know the details from the manual. ABS, absolute values, cosine, or sine are supported. Please pay more attention to the yellow highlighted functions. You can find the examples in Expression Handbook. These are also frequently used functions. These are for the calculation of displacement or angle between two markers. For example, this function calculates the x-directional displacement between two markers. The usage of other functions are similar. These are the functions to calculate the velocity and acceleration between two markers. These are the functions to calculate the force or torque using the base and action markers of joints or forces. These are the special functions to obtain the reaction force or force applied to action body. These are the functions to calculate the differential and integral. This is to use the conditional statement. It was already introduced in the previous demo video. For example, you can use if and time to define the conditional statements for time. Please note that RecurDyn uses very small value called if tolerance instead of 0 to avoid the numerical error. You can change the magnitude of if tolerance in simulation setting dialog. These are interpolation functions, 2 spline functions and 1 linear function. There are more functions as you see here. Among these, step function is frequently used. You can make this kind of curve using step function. As you can see, x usually time and x0 and h0 and x1 and h1. This is a demo video of expression. First expression is used for joint motion. It is a displacement type, so the body is moved 1000 mm by joint motion. You can see that the body moved 1000 mm. You can see the result using plot. As you can see, it is constant. If the type is set to velocity, the body moves at 1000 mm per second. The displacement of the body of the first simulation is constant, and the displacement of the second simulation shows it moves at 1000 mm per second. See? Next one is axial force. It is possible to create an axial force which has the same characteristics as the spring. (500 minus dy function is the delta of the spring. dy 2,1 is the relative displacement of two markers. I use the argument list. You can see the movement of two spheres are the same. You can review the results in plot. third one is on-off joint. This is the result without on-off joint. 2 cylinders just fall. This expression returns 1 until time is 2 seconds and returns 0. So, the two bodies are connected until time is 2, after which they fall. Next one is translational force. The body will be moved to the right side until time is 2. After that, it is moved upward. Can you see? You can change the reference marker. Since the reference marker is rotated by 45 degrees, you can see the body is moved in 45 degrees direction until time is 2. Then, y direction of the reference marker. See? Last one is expression request. The expressions can be reviewed in plot. If we want to see the result of this expression, you can define expression request for them, like this. Then simulate the model again. Here are the results of request. One more thing, you can use expression scope, like this. This was introduced in the starter kit already.